Hi, welcome to another lecture on Calculus 2. Today we are going to continue our conversation about infinite series. We are going to take a look at a bunch of problems and use the previous lecture to see what method to use to detect if the series converges or diverges. You remember in the last lecture we have 10 methods. Every now and then one of them is much better than the other ones, and the question is which one of them do you use to go after the issue of convergence. Let's take a look at the problems I've chosen for you. So I've chosen 6 problems so that we'll be able to do it in a short lecture. The question is, well, how do you test for convergence of these series? What method would you use? So perhaps a good thing for you to do is just to pause the video, investigate these 6 problems, decide for yourself how you want to proceed with respect to testing them. It would be great if you actually go all the way to the final conclusion for each of them, or for as many of them as you can, and then you come back. For each of them I start giving some clues, and maybe you can pause again and perhaps either change or correct the approach that you had. Okay, let's go look at the very first one. Question is, how would you test for convergence of this? There are 2 clues in this problem. One is it's minus 1 to the power of n. That of course makes it to be an alternating series. So we might want to go after the alternating series test. Let's go ahead and check to see what is required there. Do you remember what was required for alternating series? The terms of series have to be established to be declining and going towards 0. If you can show that, then it will be quick to go after the final conclusion. The problem is, well, showing that these terms are going to decline is not going to be easy. We haven't got enough practice with the factorials and such kind of creatures. So the question is, what's plan B? Is there something else that's going to be faster than this? Let's go ahead again and let's see which one of these things do you think is going to be applicable. Well, that series is made out of a lot of multiplication. So which one of these testing methods is built on the concept of a lot of multiplication? So of course, if you want to handle the multiplication, the best thing to do is a ratio test. So in the ratio, you're going to take a ratio of the next term to the previous term, and the way that problem is made, there's a good chance that we get quite a bit of cancellation, and then we will be able to take a limit of the ratio. If the limit is less than 1, we know that the series converges. Otherwise, if it's larger than 1, it diverges, and if it is 1, it's our unlucky day. We have to go to plan B to figure out some other way of doing it. So let's go ahead and take a look at the problem. Okay, for problem 1, so our term an, this is our nth term. So it's minus 1 to the power of n plus 1 n factorial, and then 1, 3, 5 all the way to 2n plus 1. Now if the formula itself looks a bit odd to you, the best thing to do is to write a few examples of this thing to understand what's going on. So for example, if I ask what is a3 means minus 1 to the power of, the next number is going to be 4, 3 factorial, and who's in the denominator? How do we understand this? It looks like all the odd numbers all the way up to the last of them is supposed to be 2n plus 1. This n is the index that you have here. So if n is 3, it means that we want to stop at 7, because 2 times 3 plus 1 is 7. So in that case, that's going to be 1, 3, 5, and 7, and so on. So you write a few of these things to see if you have Let's try again. A4, what would A4 be? -1. You go ahead and write it. So pause the video. So that the idea we had was that we want to pause this thing and you try to practice the problem and not to be just a listener. So this is going to be 4 factorial, and we see that the denominator is 1, 3, 5, 7, 9, and so on. So the idea of a ratio test was to take a ratio of the next to the previous one and figure out what that would be. Let's go ahead and practice this simple case, A4 over A3. Okay, over there we have to do an plus 1 over an. Well, let's do a simple case so that we know what is involved. So that divided by this. Well, how do you divide two fractions? You divide by multiplying with the reciprocal. So you have to take this. So I have -1 to power of, I forgot to write, there's a 5 here. -1 to power of 5 times 4 factorial over, and then we have 1, 3, 5, 7, 9. And then we have to multiply by a reciprocal, so it's going to be 1, 3, 5, 7 over -1 to power of 4 times 3 factorial. You see how nicely they are going to cancel each other out, because 1, 3, 5, 7, 1, 3, 5, 7, they cancel each other out. What is 3 factorial? It's 1, 2, 3. What's 4 factorial? 4 factorial, 1, 2, 3, 4. So of course all of these things go with all of those things. And who's left? Is a 4 left and 9 is left here. Minus is one power is more than the other one, so a minus survives, a 4 survives, and 9 survives. So that gives us hope that we can actually simplify the ratio. So that's why we went after the ratio test. It's actually possible to simplify the ratios, because this is made out of multiplication. So when you divide them, they cancel each other out. So this -1 times that. In the ratio test, you have to take the ratio, take the absolute value, which of course is going to be 4/9. And the condition there was that if the ratio, the limit of the ratio is less than 1, then we have convergence. Well, this is in a single case. In this case, the ratio is less than 1, but that's a good indication that in general that's what's going to happen, that the number in the denominator is twice that plus 1 because of this 2n plus 1. So let's go ahead and show that in the general case. So I write an plus 1. An plus 1, how do I write it? The trick is to take all the n's in the original problem, replace all of them by n plus 1. That's going to do it. So -1 to power of, let me write it in a different color so you see what happens. That all the yellow stuff is going to be turned into this red stuff. So it is going to be n plus 1, and then you have to put it in parentheses so you don't misunderstand that. And in the denominator, 1, 3, 5. Instead of n, I have to write n plus 1. So I write n plus 1 and then plus 1. So that's what an plus 1 is going to be. We have to take the ratio of these two. Before I go any further, let me clarify some basic things. Sometimes the student get confused as to what does this thing mean really. What is 1, 3, 5? Are you multiplying by dots or what? What's going on there? So it has to be understood. Start at 1, multiply all the way up to 2n plus 1, and whatever is needed in between, just include them. So if you are at the very beginning, for example, you are a0, well, a0, term number 0 is going to be -1 to the power of 0 plus 1, 0 factorial over. Start at 1 all the way up to, well, this is it's still 1, so that's just 1. And remember, 0 factorial was 1 also, so this whole thing boils down to just -1. How about a1? Let's go write that also. -1 to power of 1 and 1 is 2. 1 factorial. If I put 1 here for n, I'll have 3 means I'm stopping here. So that's our stopping place. Of course, there's no more 5s in the picture. 1 times 3. And if you have a2, it's going to be minus 1 to power of now 3 times 2 factorial over 2. When you put the 2 here, you are stopping at 5. That's now your stopping place. 1, 3, 5, and so on. So write a few examples of this thing to make sure you understand what is meant by that formula. Okay. Next, what do we want to do? We want to calculate an plus 1 over an. Simplify that, take absolute value, take a limit, see where it goes. Okay, how do you do that? I have to take this thing, divide by that. How do I do that? Well, this times reciprocal of that. So minus 1 to power of n plus 2, n plus 1 factorial over 1, 3, 5, all the way to, simplify this, 2n plus 3. Dividing by this means multiplying by reciprocal, so that's 1, 3, 5, 2n plus 1 over minus 1 to power of n plus 1 times n factorial. Okay, if you didn't do the problem before, let me urge you again to go ahead and simplify this fraction before I do it. So it's an important thing you discover for yourself. So minus 1s, they cancel, so one has one extra power than the other one, so that just boils down to minus 1, just like we had a minus 1 here. N plus 1 factorial, n factorial, how do they take care of each other? Well, n factorial means 1, 2, all the way to n. N plus 1 factorial means 1, 2. You reach n, you don't stop there, you go one more, n plus 1. So when you simplify, this portion, that portion cancel each other out, you have just n plus 1. N plus 1. Well, how do these two simplify each other? This one goes to 2n plus 1. This one goes to 2n plus 3. 2n plus 1 is the parenthesis just before this. Let me rewrite this thing so you see what is meant by it. So we are starting from 1, 3, 5, all the way. Then there is going to be next odd number 2n plus 1, next odd number 2n plus 3. When you simplify, all of these, all of those cancel each other out, and you are left with a 2n plus 3 in the denominator. It's very crucial that you get used to this algebra, make sure you understand what's involved. Okay, now if I take absolute value of this thing, all that happens is that my minus is going to go away, so that's all gone. Next, what's the limit of this? Limit of this, as n goes to infinity, well, you have seen this thing in pre-calculus, is 1/2. Okay, so that means essentially as you go toward the tail of the series, next term is going to be half of the previous term, approximately. Next term is approximately 1/2 of the previous term. So it's our sequence kind of dominated by a geometric series, and that's why it converges. So if the limit is less than 1, here is our final conclusion, that this thing converges. So 1 down, 5 to go. Verdict for this thing, first of all, we use the ratio test, and then we concluded that it converges. We didn't go after the alternating series because that would have been more expensive actually. Okay, up to problem 2. So we have 5 more of these things. Again, let me urge you to go ahead and do it yourself. What do you think we should do here? So we have some complicated thing. Which one of these? So we think about some way of reducing the complication of what we are facing there. Over there we had power of n. When you have a power of n, almost sure that the root test is gonna be the winner, because you're taking the nth root that's going to cancel out that exponent, and hopefully the rest of the problem is easy to handle. Let's go see if it is really so. So uh, here we say this presence of this exponent tells me good thing to go is a root test, and that's going to be in fact a lot faster than the previous one. So let's go ahead and so next problem is take logarithm of n over n to power of n, and check that. Well, at what n do you want to start? Not that it matters for the convergence, but just good to know. At n equal to 0, we are going to have so many problems. Logarithm of 0 is minus infinity. Division by 0, wow, that's going to be another problem. Power 0, 3 strike and you're out. So we might as well forget about that and go after n equal to 1, and 1 this is 0, so that first term is 0, or you could start at 2 if you want. Either way, so one thing was important, 0 is hugely problematic there, so we just skip that. N equal to 1, you can start at 1 or you can start at 2. Now we said we are going to look at the nth term. Nth term is this complicated expression. What was the root test? Root test was that if the limit of an to the power of 1 over n, you put in absolute value, is less than 1, we are going to have convergence. If it is larger than 1, it's going to diverge, and if it is equal to 1, we have wasted our time with our test. It doesn't tell us anything. It's inconclusive. Well, what is an? First of all, our an's are positive, so let's reduce the clutter here. An to power of 1 over n. So if I have this logarithm of n over n to power of n, the whole thing raised to power of 1 over n, of course, nice thing, reason we chose this is that these two cancel each other out, and we have logarithm of n over n. Okay, next issue is what's the limit of this? How do you get the limit of logarithm of n over n? That is something from calculus 1. Hopefully you're up to speed with respect to that. You probably remember that there is a pecking order between the functions. Logarithms are like the stepchild. They are kind of, logarithm of x is very much smaller than x to any power, and that is much smaller than exponential of x. So this double inequality is saying that when these things go to infinity, how much bigger is the next infinity compared to the previous infinity? Okay, if you wish to think about it like having maybe sumo wrestlers, maybe this is 300 pounds, maybe this one is 500 pounds, and so something like that. These are all, when x goes to infinity, these are all going to infinity, but there is a difference between infinities, and some of them are bigger than the other ones. So that's like a very general rule of thumb for talking about them. You get familiar with that in calculus 1. More formally, what do you do? More formally, you say, okay, I have logarithm of x over x. Instead of n, we just put an x for a continuous variable, and I'm taking the limit of that when x goes to infinity. Well, a powerful tool that you have from calculus 1 is what? What do? You take, of course, L'Hopital derivative of logarithm of x is 1 over x, derivative of x is 1. You take the limit of this when x goes to infinity, and that limit is 0. Means the limit of this as n goes to infinity, since it matches that, the limit of this one is also 0. And what is it that we wanted? All we now wanted is for the limit to be less than 1. This is like the best we could hope for a positive number less than 1 there, well, the smallest one is 0. So since this is 0 and 0 is less than 1, our final verdict is that our series is going to converge, because that was the statement of the root test. So this case was quick. We applied the root test, and the conclusion was that it is a convergent series. Next up, how about this one? Which method do we use to go after this? Well, you have several choices. You can, once again, let me insist that you try to tackle this yourself, and then come back. Okay, so we have again 10 choices. Which one will be helpful for me? Well, if you want to go ahead, nth term series, well, I know that my nth term goes to 0, but that doesn't tell me anything. It's not geometric. I cannot do anything about it. Doesn't look like telescoping. I cannot break it into a subtraction. Let me clean up the where I have. I don't know what happened here. Well, it's not a pure P series, even though it's close to it. Obviously, it's not alternating. We can think about integral test that is available to you. Of course, you have to be able to actually calculate that integral. So that is one way you could go. X over 2x squared plus 1. Do you feel comfortable with that? That is one option you have to go after this one. Root test, I don't have a power in there to handle, so this doesn't look like applicable. Ratio test, these two, whatever you apply here, you're going to get stuck with this unpleasant, inconclusive, so you have ended up wasting your time. What you can do is do direct comparison or the limit comparison. Limit comparison is perhaps easier because you don't have to worry about establishing inequality either. So two methods to go after this problem. One is integral test. Integral test is good when your elements are positive, continuous, and decreasing. To establish decreasing, you have to establish an inequality. So that takes a little bit of work for our problem. If we want to avoid that, if you want to really be quick and go after this problem as fast as possible, the best thing to do is this limit comparison. Limit comparison is going to be the fastest route to getting an answer and not get bogged down with all intermediate steps. So if I want to compare this thing, limit comparison, what's a good comparison? Well, for this rational function, the easiest thing you can do, take the leading exponents, simplify that, you say 1 over n, compare this thing against that one. So here is the style we are going to apply this. It's going to be limit comparison, and it's going to be compared against what? Well, when I simplify this, I have n over n squared. N over n squared simplifies to 1 over n. What's your verdict for the sum of 1 over n? You remember what series that was? That was the harmonic series that diverged. So this thing looks like our verdict before we actually go to the detail of it. This is going to diverge. Let's go ahead, write down the steps. So n over n over 2n squared plus 1. You can start from 1 or 0 or something and go to infinity. So our an Okay, it's a simple approach to that applies to all so-called rational functions. You have a polynomial here, you have a polynomial here. Just extract the leading power in the numerator, extract the leading power in the denominator, simplify that. That's just 1 over n. That would be your uh, comparison series. Comparison series is simply 1 over n. That is, sigma of 1 over n is going to be compared against this one. Okay, so you simplify the leading term, you have your new series. It's 1 over n. You know 1 over n diverges, and that's going to be why this one diverged. So I'm going to take b over n, bn as 1 over n. We take a ratio of these two, bn over an. So it's 1 over n. Let me write it the way you write it in school, and then simplify 1 over n over n over 2n squared plus 1. How do you handle this? You take the numerator, multiply by the reciprocal of the denominator. Is that right? Isn't that what you do? Let's clean this up. 2n squared plus 1 over n squared. Okay, both series positive terms. We took the ratio. We take the limit of this thing. What's the limit of bn over an as n goes to infinity? This thing, you have done plenty of that in calculus 1. So you should know what this limit is right off the bat. Or if you remember, forgot, apply L'Hopital or divide or whatever. You take a ratio, you take a limit, you just get 2. What does that mean? If the limit is any number between 0 and infinity, so 0 is not acceptable, infinity is problematic for us. Any number between 0 and infinity, what does that tell us? It means these two series share the same fate. So if you know what's happening to the sum of 1 over n, exact same thing is going to happen to the sum of the other one. Well, this one you know from p series or harmonic series that it diverges. Therefore, the first one, so we write like this: I know that sigma of 1 over n diverges. That, given the fact that this is some number between 0 and infinity, it means the other one shares the same fate. N over 2n squared plus 1 will do the same thing. It will be in the same neighborhood of this one. That's what the limit comparison means. The two of them are going to go hand in hand. One is just double of the other one. So if one of them goes to infinity, this one will be same type of infinity. Maybe it's just half as big, but it will be infinity too. So that's going to be diverging too. So our conclusion here was that it is we are applying limit comparison. It's going to diverge. Okay, now what about item number 4? What do you think is going on here? Which one of our tests seems to be applicable? Again, it has a 1 minus 1 to power of n. That is kind of a bit of a maybe banana peel, I should say, like that. It's like you might see that immediately, say, okay, this is alternating, and pretty much everything alternating I saw is converges, so this one converges. Of course, that is totally incorrect. Let's go carefully look at what was. For alternating series, one big deal is to show that your terms are decreasing and going towards 0. They better go to 0 anyway if you want to show that something converges. If it doesn't go to 0, it doesn't converge. So here we have two issues. Is it alternating? Well, yeah, it is alternating. That does not mean automatically that it's going to converge. We look at this section, you see that this is 3 over 2. This is growing by factor of 3/2 or 1.5. The terms are magnifying as you go down the line instead of going towards 0. So by the nth term test, this thing would not converge anyway, and that alternating doesn't help anything. So the test we apply, easiest test to apply is the nth term. This ratio 3 over 2 to power of n going to infinity as opposed to go to 0. So by the nth term test, this thing is going to diverge. Okay, I'll let you fill in the details. Cosine of n over n cube. What do you think we should do here? Well, again, for the 5th time perhaps, insisting that you try to do it yourself and come back. First, is this alternating? Well, no. In the numerator, cosine sometimes positive, sometimes negative, but not as in a flip-flop style. It is going to be a very complicated pattern of pluses and minuses in the numerator. So it's not alternating, but it does change its sign from n to n. Okay, then what? Then we say, well, perhaps if I compare this thing against another series. So what series is it? So cosine of n, I don't know what's going to do, but I know cosine is always less than 1. It's between 1 and minus 1. So this quantity is between 1 over n cubed and minus 1 over n cubed. And those converge by the p-series test. 1 over n cubed converges. So this one will converge by direct comparison and by absolute convergence. So this one converges by direct comparison. And the conclusion will be that is going to converge. Let's go write a little bit more about this thing. So remember, one of the facts that we had was that if absolute value, sum of the absolute value, if that one converges, if I know sum of absolute value converges, then some of the numbers themselves are going to converge. Qualitatively, how do we know that? The numbers could be positive, negative, they could cancel each other out, and that's going to be even more of a control than just adding positive numbers. So this one has a better chance of converging than that one actually. Okay, next we are going to say I want to investigate cosine of n over n cubed. Say, okay, instead of that, let's consider cosine of n over n cubed. Put it in absolute value so that I force everything to be positive. Next, I compare this thing versus sum of just 1 over n cubed. Well, I say this, the terms here are less than the terms here. I know this one converges. I know this one converges by p-test. P-test said if the exponent is more than 1, it will converge. So this one converges. This is that is less than that, less than something that converges, then this one converges. And if absolute values converge, the original converges. So maybe this style of reasoning in mathematics is a bit unfamiliar to you, but that is something to get used to, especially if you're going to go higher level theoretical engineering or mathematics itself. So our conclusion was that in this case the series does converge. We quickly diagnosed that. Last item we are going to look at, to keep this video short, we have the issue of how about item number 6, logarithm of n over n squared. What do we do with that? Well, what is it that doesn't apply? Well, nth terms doesn't apply. The ratio goes to 0, but that does not tell me anything. It's not geometric. It's not quite p-series because numerator is a logarithm of n. So what is left? How about comparing against 1 over n squared? Well, that's a wrong comparison because this is bigger than 1 over n squared. So you still can play with comparison, but perhaps an easier one of tests to apply. Let me see if you can guess which one is going to be a good logarithm of n over n squared. Integral test is a good way to attack this problem because, well, that's the kind of integral we have seen and we are likely going to be able to handle that. So what we are going to do, going to apply integral test. Well, that's going to kick us back to what we had a couple of months ago. Here is, might feel like jumping from frying pan into fire, but well, let's go ahead and jump. So logarithm of x over x squared. What was the story? If this improper integral converges, then that one converges too. If that one diverges, this one will diverge as well. So they go hand in hand. So if we have two functions, both of them positive, declining, then we can do that comparison. Let's go ahead. Insist that we actually have we have a function that is positive, continuous, and decreasing. Then we can apply this test to it. So let me leave some of that detail to you, and then maybe help you with the integration. But this is a problem we have seen several times before. Let's see. So integral of logarithm of x over x squared. The functions match. You have to show this function is a decreasing function. So at least from some place on, you have to show it is decreasing, and then you have it made. So dx. How do you handle that? Of course, that was one of our basic substitution and integration by parts problem. So I take u to be logarithm of x, everything else that's left is dv, and so my du is 1 over x, and my v, of course, is going to be the antiderivative of this thing is minus 1 over x. So uv is going to be minus 1 over x logarithm of x, and minus v du. v du is going to be, well, v, oh, I forgot to put my dx here. v is minus 1 over x, and du is 1 over x dx. Is going to be minus logarithm of x over x, and then this is going to be plus so if I want to calculate from 1 through infinity of logarithm of x over x squared dx, to see what that integral is going to be, I have to put, let's write all of this thing in nice fraction, minus logarithm of x plus 1. Excuse me, let me put the it's going to be misread. Maybe I should have left them separately. Yeah, let me write it like that. Well, at infinity, logarithm of x over x, you apply L'Hopital rule here to see that is 0, just like this one is 0. So at infinity I have 0 minus at the 1. At the 1, this is logarithm of 1 is 0, and this is minus 1. So that integral becomes just 1. So the improper integral converges. So if this one converges, the other one will converge. The only thing that's left to show is to show that the function f of x, which was logarithm of x over x squared, we have to show this is decreasing. Typically the easiest way to do that is to take a derivative and see what we get out of that. So I have f prime of x, derivative of numerator is 1 over x times denominator, minus denominator times the numerator over denominator squared. So it's going to be x minus 2x logarithm of x over x to the power of 4, or 1 minus 2 logarithm of x over x cubed. Well, this thing obviously eventually becomes negative. At the beginning maybe it's positive for a short while and such, but as time passes by, as x gets larger, that of course logarithm of x is going to become bigger than 1/2, and then that function becomes negative, and that tells me my f of x is decreasing, which tells me my test is a valid test. So this is a extra technical step to go through to make sure that your comparison is legitimate. So this one, the final conclusion, final verdict, this one was integral test, and it was converging because that integral did converge. Okay, there are like about 50 of these problems in your textbook. Good idea is to go through, well, I guess I'll be dreaming to say to do all of them, but do a few. Until next time, good luck and God bless.